So good morning to all of you. I welcome you all in the 5th day of Indo-US Webinar and the Lecture Series. I again welcome our eminent guest and scientist, Professor Mao, for joining with us continuously and delivering the excellent talks on very hot topics. Yesterday, he delivered on hydrogen storage, and everyone, including us, enjoyed a lot in his lecture. Today again, he will talk about the nuclear waste containment. This is again a very important topic when we talk about the energy. So with these words, I request Professor Mao to please start his lecture. But before to start his lecture, I would like to inform to all the participants that it is a 2 hours lecture, which seems to be very long. So we will have a very short break at around 11 o'clock. So the break time will be decided only by Professor Mao. But the break time will be for 10 minutes, right? So it will start at 11 o'clock or 11:05 or 11:10. This is up to Professor Mao. So with these words, I request Professor Mao to please start the lecture of nuclear waste containment. Thank you, sir.
Thank you very much, Dr. Ahmad. Thanks for the introduction. And so, yeah, today we will start with a new topic, and it's on nuclear waste containment. But before we go that, I want to show you some background information, especially start with the introduction about the nuclear energy, and then, why we need to talking about the nuclear waste containment, basically was a part of the nuclear waste storage. So we need to understand the radioactivity effects, right, of nuclear waste. So, and of course, we were looking into different type of nuclear waste. And then, we'll talk about the different strategies to store them. So that's briefly, what we plan today. And yeah, nuclear energy is I believe we heard about it here, there, maybe we have mixed feelings about it, right? So that's what I'm saying here, the good, the bad, and the ugly. We will talk about each of these aspects. Okay, let's start with that way. Nuclear energy, right? It's basically the energy that exists within the nucleus of an atom. There are 2 types of nuclear energy. One is called the nuclear fission, which is the splitting of a large nucleus, which were releasing a huge amount of energy. Then the other one is a nuclear fusion, is a compilation, right? Fusion, that means it's a compilation of smaller nuclei to form a heavier nuclei. And that also were releasing huge amounts of energy as well. So later on, I will show you some calculations. Actually, this both is a huge, right? Huge amount, releasing huge amount of energies. And we'll see which one is actually even more in terms of mass weight. And also one thing we need to realize is right now, actually, most of the nuclear reactors use nuclear fission, not nuclear fusion yet, which is something is still working on. But yeah, that's the other thing. So first, we need to understand nuclear energy, right? So compared with chemical bonding forces, and nuclear forces stronger, equal, or weaker. Right? I think that's something it should be easy to understand, but it's something important for us to realize it first, right? Because of the nuclear forces are much stronger, so the energy released per atom in nuclear reaction is immense compared with that obtained in combustion reactions, right? Combustion reactions mostly is because we are breaking the chemical bonds, right? So this actually, this one shows, describes the fusion splitting of uranium atom. So we will talk about the uranium quite a lot today. So basically, to initiate the nuclear reaction, and so we will irradiate the uranium 235 with neutrons, and then this uranium atom will be split to lighter elements. But at the same time, is the important thing is it will release energy, right? That's what we keep saying, huge amount of energy. And at the same time, is they will be releasing some of neutrons. And then these new neutrons can be, started to irradiate the uranium again. So we'll talk about this a little bit more. Depends on how these neutrons are being controlled. So that's basically the fission reactions. And then for the fusion reactions, then two lighter element atoms, and they combine to a heavier element, and then release energy. So that shows how this process is. At the same time, it's releasing neutrons as well. So for that, then we get back to the fission process a little bit more. Most commonly used is the uranium-235, right? Start with a neutron and combine with this uranium-235, and then break down, split into two smaller atoms, and then release 3 new neutrons. So these are the two ways to show this process, right? So uranium, and then we know the natural abundance is actually the uranium-235 is only about 0.7%. Then majority of uranium is uranium-238. And then, yes, the uranium-238 also can have this type of reactions. So if we hit uranium-235 by a neutron, and then, it produces a uranium-235, it goes through this process, it eventually becomes pollutant. And so that's the process, then for uranium-235, then, it generates more neutrons, and then this reaction could keep happening. So that's the, and then from uranium-235, it generated proton-239, and which also can keep happening, and then, the reaction happen, we eventually go to this. The question here is, right, uranium-238 is much more abundant, right? Why don't we use the uranium-238 for nuclear reactors, nuclear energy, right? This is because you can see here, right? If we hit the uranium-238 by neutron, and it doesn't generate, more neutrons, and also the release the energy from this step, this process is much less. So that's why for nuclear reactors, we use a uranium-235. And then, this is the other process, it gives us this chain reactions, more clearly. I really like this way. So start with the uranium-238, and then it goes through this way, and all the way go down to lead. So lead eventually is non-radiative. So if it's lead 206, and so that's the in the process it generates a lot of actinide products, a lot of radioactive elements. So that's something we're talking a little bit, how to take care of this. That's why we need to talk about nuclear waste containment. So in terms of nuclear fusion, these are the different type of reactions, right? So you can see here, the deuterium and combine with the deuterium, and then it generate helium, and then 1 neutron, and it gets back to tritium and hydrogen proton, right? So if it's that's those reactions are the common ones, right? If it's a deterrent and the tritium, and then it generates helium-4 and 1 neutron, and so that's how this is for the fusion reactions. And so related to this, right? There are some other related reactions, right? If what is for example, right? I showed you a couple of equations like this now, right? Hopefully, we can work on some new fusion reactions, right? For example, if they are helium-3, right? What are the fusion reactions, involved with it? So these ones are actually called the advanced fields for fusion reactions. So still deuterium and helium-3, and then this is the reaction. And then if two of them react with each other, and then it will generate two protons. So then if there are some other fusion reactions as well. For example, the helium-4, if it is bombarded with lithium-6, and by bombarding lithium-6 with a neutron, and then how this generate the tritium and the helium-4. So this is the type of reaction, and of course during this process it will release energy. That's the fusion reactions. I try to show you a couple of examples like this. So because mostly, right, even when we take chemistry classes, right, we normally don't talk about the nuclear chemistry. So I think this is a little bit important to understand this. This is this exercise is long, so I don't expect like you spend the time to work on it, but I will show you the answers, so because of the time. But the important thing is that let's go through this question first, right? How do we calculate the amount of energy released in the fission process? So and then later on we will compare with that for the fusion reaction. Okay, so the important thing is, this is the reaction related to uranium-235, right? I showed you a little bit earlier, and then it generates barium-142 and the Compton 91, and then also 3 protons. So how do we do this? Is you see here we have the atomic mass, right? So from Einstein that equation, so we know that, right? So E equal to mc squared, right? So first, the important thing is we need to calculate what is the mass change, right? So the mass change from this reaction is this is uranium-235, right? So and then minus this, and there's a barium, and then also there's a Compton, and then because this is 1 neutron on this side, 3 on this side, so now it becomes 2, right? And then the mass change is 0.188 grams, and so then we use E equal to mc squared, right? And then because this is only and also then this is the speed, right? The light speed, and then eventually get so many joules, right? So that is for so so that is for the energy release based on this this equation, and also this is for 1 molar, right? For 1 mole, and then if we divide this by the mass of reactant, right? So that the mass of the reactants, that's one thing we need to realize. So this is the new number, basically is the mass of the uranium-235 plus the mass of 1 neutron. So that's why you see here now this is 236.05, and that is that equals to 7.16 times 10 to 10 joule per gram. Okay, so this is from the fission process, right? We can do the same for the fusion reaction. And so I'm not going into the details, but eventually we do the calculation, and then now you will see this is a 10 to 11th, okay, joule per gram. So that's why I mentioned a little bit earlier, the fusion reaction is actually gives more energy in terms of the in terms of the mass. But there are, technically there are a lot of challenges. That's why fusion reactions hasn't really, commercialized. So then the other thing is, let's get back to the fission energy, nuclear fission energy. So this is schematically showing the fission reactions, right? As I mentioned to you earlier, we have uranium-235, is bombarded by neutron, and then it becomes two daughter nuclei, and that's which are the lighter elements, and release a lot of energy, and then it generates, by one step of this, right, it generates three new neutrons, and those neutrons will hit uranium-235 atoms again, right? And then it keep going, so this will expand, this reaction will, expand exponentially, right? And then, of course, it generates a lot of energy, but at the same time, we generate more and more neutrons in the reaction, and then that will speed up the reaction, right? So that's why next slide I will show you this. This is normally for nuclear reactors. That's what we see, right? But if the reaction here is not controlled, if we let it just react like this way, and this is what will happen, right? So we call this is controlled nuclear fission reaction, and this is uncontrolled, right? Of course, we wanted to keep it under control. And also today we are talking about the issues related to controlled nuclear fission reactions. Okay, we don't want to talk about this uncontrolled. That's not our business today. I hope for humankind, will never let this happen again, right? That's the other thing. So the fission nuclear power plants, and that's what we will spend a little bit of time now. So again, right, this reaction happens at a controlled, manageable pace, and then release energy slowly, right? So that's important thing for us to keep in mind. And then the generated heat, then we can use it to boil water, and that creating steam. And once we have the steam, then that's how do we generate the electricity, right? The steam turns turbines, which rotate the electrical generator and create electricity, right? So this is the key part for nuclear reactors, right? And then so this is schematically showing that. So the turbine, and then generate electricity generator, and then we get the electricity, and then go to our houses, right? Of course, we normally live far away from the nuclear power plants, so we don't see it. And but this is the process. So with that, the fission power reactors, and I keep showing you this reaction, because this is the most important reaction for this, right? So if we show this again, right, we want to show the whole process, because the one we showed you earlier, this is generate the electricity, and then we use the electricity. That's it, right? But related to today's concept, the main topic, we need to go a little bit further, right? So here, generate the heat, and then the power generator, and more importantly, we need to look in this part, right? So basically, right, they are the fuels. The fuels here we talk about the nuclear fuels is the uranium-235, right? So this part, after the reaction, after a certain time, then we have spent the waste, and which is spent, those are the leftover of the uranium-235. And so normally, in this in this nuclear reactors, right? Those are pretty hot, and also because they are radioactive, so we need to cool it down. So normally this happens in a pool. Okay, it's not our swimming pool, but that's how we keep this cool. And then after a while, then we have to dealing with the nuclear waste. And in current technology, this waste is sealed in dry cases. So we'll talk a little bit more details. What's the challenges with these processes? What we need to develop, with new technologies. So that's basically the process. So also related to this heat generator and this part, right? And I want to show you some quick calculations, right? So if we want to calculate the percentage efficiency, right? If we convert in the heat, for example, if we convert the heat, right, at 300 C into electricity, according to the second law of thermodynamics, okay? Of course, we can assume the cooling water is at 17 degrees Celsius. So I want to skip back to here, show you where the cooling water is, right? So here is the turbine, right? So this is hot water, right? Goes to the turbine, eventually it gets to condensed and it gets to cooled water, right? So the temperature here is, we assume is 17 degrees C, and here is 3. For this question, it's 300. Okay. So we also can repeat the calculation if that high temperature is 550 degrees Celsius. So to do this, this actually is this is a equation we can use. The heat converted divided by the initial heat, right? So the heat converted basically, related to the high temperature minus the lower temperature, and then divided by the high temperature, and then we got the maximum percentage efficiency is the same 49%. So if the heat, the high temperature is 550, and then let's see, how this conversion efficiency is, and it actually becomes 65%. So technically it's important to get to higher temperature, and so that's what we can base on that. And then the fusion power reactors, this actually table shows the nuclear power around the world. This is based on the number from 2011, and you will see United States has 104 operating power reactors. France has 58, and then India has 20, and then Great Britain 19, Ukraine 15, China 13, Sweden, and then there are some other ones, 63. But the important thing is, the proportion of electricity generated by nuclear power, even though United States has the largest number of operating power reactors, because United States is large, so the generated electricity generated by nuclear power is only 20%. Of course, this also depends on how big the reactors, right? And then France is only have 58, but France, the electricity is generated by nuclear power is 74%. So that's pretty high, right? And then let's see, Russian is 17%, Indian is only 3%, right? And then Reddiver 16, Germany 28, Ukraine 48%. That's also pretty high, right? China is only 2%. Sweden is 38%. Okay, so especially Indian and both Indian and China, we have a larger population, and and also compared to, especially with France, right? There's a huge way to grow, a huge room to grow. But why we don't, right? So that's related to today's topic. And so this is actually the fission power reactors in US. You will see that mostly on the East Coast, the Midwest, and then the West Coast. Not many in the middle in this region. And in the state where I live, there are actually many reactors. I didn't know this before, and then you will see here, right? There are many around this area. One is very close, which is called the Clinton Power Station. So Chicago is somewhere here, and this is where the Clinton Power Station is. This is not really a big one, but it's close to where I live. So anyway, nuclear power produced, it's again is an extremely rich energy source, right? If we really look into the numbers, 1 gram of uranium-235 delivers as much energy as 3.5 metric tons of coal, right? So you can see the big difference, right? How many tons of coal we need. Then in 1 in every 5 houses in the US is supplied with nuclear energy. Again, for me, I didn't know that number, right? But if we go back to this table, that's 20%, right? So that's exactly 1 to every 5 families. So these numbers are 1 in every 5 houses in the US. Okay, and then the pros of nuclear power, is a rich energy source, right? Again, we talk about this number, right? Because of the coal generate a lot of greenhouse gases, a lot of those issues. So that's why, there's still, people talking about, I want to develop more nuclear reactors, right? And then also the reactors run for years without refueling or being shut down and need little maintenance. This is a relative term, okay? So we will talk a little bit about this. And then no air pollution. So that's also, why, people still like nuclear energy. And but there is also, the main problems with nuclear power is it produced radioactive waste. That's what we are going to talk more today. And the big problem is, yes, there's a lot of energy source generate waste, right? But this is radioactive waste. The main thing is there's no permanent long-term disposal site for commercial nuclear waste. I'll get into more on this. And especially in US, this is a big problem because, let's wait a little bit, I'll get into that. There are relatively short supply of uranium-235, right? Only enough left for 100 or 200 years. Again, right, and I showed you earlier, right, uranium-235 has a very low abundance. But recently, I just published a review article about how to connect, how do we get enriched uranium-235, for example, from seawater, right? So the numbers here, we are mostly talking about, what is available on land, but there are large amount of uranium-235 in seawater. But then the question is, because it's so dilute, right, in seawater, and there are tons of seawater, right? So how to connect them, that's also a challenge. So of course, there are some material challenges to do that, and there are some research on that. So then the nuclear power plants are expensive to build, okay? That's also a concern. The minor maintenance problems can be very expensive to fix, right? As in the previous slide, we say, there's no maintenance, but when there's a maintenance, then it's very expensive. Safety concerns, and the safety we'll talk more, not just the explosion by itself, okay, generally it has some health safety issues as well. So that's basically, that's the introduction to nuclear energy. I hope it gives you a little bit idea about, have a little bit clear idea about nuclear energy. And then the next thing is let's talk a little more about the radioactivity effect. So this effect, okay, It's not just, to, we don't have a accident, a nuclear reactor accident, okay, but, it also related to the effect on our environment, health, and energy supply, okay. So that's what I meant. In the past, there are a few big accidents. For example, in the US, there is one. It's called 3 Mile Island, which happened in 1978, and then this one, Chernobyl. This is the one happened in Ukraine, and in 1986. And then the most recent one, you probably heard about it, Fukushima, and it happened to 2011, right? So these are the big ones, and of course, then there's the next question is, was there any other accidents? Of course, there are other accidents, but not as big as these three. And in general, now, if you see this sign, okay, never get close to it, right? This is 2007 ISO radioactivity danger symbol. Okay, so yeah, the red color, the background that indicates that is urgent danger, right? Normally we see some of these danger signs, right? It's yellow, right? But this is red. Okay, that's we can imagine. And this one, Chernobyl meltdown in the former Soviet Union. The countries actually died from the radiation explosion, and the thousands contracted cancer from high level of radiation exposure. That's one really. Then this one mentioned happened in the U.S. This not this is mild. It's not really big, like so many people get hurt, but it's really put everybody, in concern. And then, actually, I want to get back to this, right? This is why, recently we wonder, it has so many advantages of nuclear energy, right? Why don't the world build more nuclear plants? So this is related to the public, awareness and how public accept this type of energy, right? So there are some reports, there are some studies, so you see these two accidents, big accident happened in the 1970s, 80s, right? And actually, the public acceptance of nuclear energy was getting better, but then all of a sudden in 2011, and then there's a huge accident happened in Japan, okay? And then, people are more concerned about the safety of nuclear power. So that's why in the US, for example, people are concerned to build more nuclear power plants. So this type of thing, it's very important for us to consider multiple aspects. For us as a scientist, normally we don't, in general, we consider more about the technical challenge, and the technical achievement. But to get this type of technology employed, actually, we have to think about how the public awareness, how the public acceptance. So that's why now it's very difficult to build new power plants, especially I think for example in the US. So getting into that, right? The other thing I want to emphasize is the nuclear, issues. The environmental issues is, and the health issues. It's not just to our humans. Okay, there's many other aspects. So here, right? For example, if we start with the radioactive material release, right? A lot of times it will happen to the air and also precipitations, okay? And here, and so if we think about the atmosphere, size, then we will understand, this precipitate will bring the radioactive materials to many, to different distances, right? And then that will go, to our humans, or once it deposited to the land, it will affect our crops, right? Then, we humans or animals take the crops, right? And then, that also. And if we deposit to the soil, right, that's also, and then eventually go to the animals and the crops as well. And animals for milk, for meat, eventually all go to our humans, right? Again, if this radioactive materials in air, then we inhale. So you can see this is a whole system. It's that's why there's so much concern about the nuclear power. But then there's a counter opinions, right? Okay, so then some people say, yeah, we all worry about the nuclear power accidents, the danger, right? But then if we think about the coal, the oil, biomass, right? The death from energy production, right? Especially if we can look at these numbers. Of course, these are the hypothetical numbers, right? The coal, the brown coal, so this let me see. So this was assumed based on the energy production death rates. So based on this unit, right? There will be 5.2 million people will die, right? But for nuclear, this number is much lower, right? And then you can see, for biomass, for oil, so in that way, the counter argument is that the nuclear energy is actually still quite safe. Okay, so depends on how you think about this, right? This is one type of opinion, So that's why, yeah, we want to keep it safe, so we can follow the nuclear reactor safety manuals, right? And we just want to show you this, but then. For example, there's a report quite recently, Massachusetts need to reconsider nuclear energy. Okay. Yeah, so, different opinion, people have different opinions, right? So where we go, that's still, for us to consider, for everybody, for general public, for politicians, and for government. And so, and then, more related to this, right? The radioactivity, there are actually two aspects. How do we arise, right? One is the actinides produced from the intact uranium nuclei. Okay, then the other ones are from the fission products generated when the actinides undergo fission. And these are the or the process, during the process, then the neutron decay continues until the product is no longer neutral rich, right? And then it's stable, right? So the ones before that, and they are radioactive, okay? So it's not just uranium nuclei, but then there are some of these fission products. So that's what this talks about. And then here, is actually showing how long it takes, right, to get this neutron-rich stable species, right? So this is actually radioactivity released. You will see that, and for example, from the uranium ore. And the important thing is this is actually about 10 years to get to these two species, right? We also heard about this. These are also radioactive elements, right? So, but of course, then after about a few hundred years, then it's more or less is stable enough. So that's why when we talk about the nuclear waste storage, we want to make sure that storage or the containment materials can be, it should be very stable, right? For 100,000 years, and that makes it's very challenging material challenge. So And then this actually describes the whole process, right? From each of these steps, and then it could generate radioactive materials, right? So here, start from the mining, right? Uranium ore, and then conversion, right, to the reactor fuel, right? Reactor fuel actually, most time is uranium oxide, and or into the uranium hexafluoride. And then, for that, we can go through the enrichment process, and then, put in reactor, and also, later on, we'll talk about the reprocessing. After the nuclear, after the fuel, depleted, and then we can go through the reprocessing process, and part of it we can go back to the reactor, and then we also, part of it will become the radioactive waste, and then we need to process that. Some of this reprocessing, it generates a plutonium bomb, and that can be used, and then uranium is also, used as a uranium bomb, atomic bomb, that's what it's called, right? So that's the whole process, the fuel cycle. And many of these, so when we talk about the nuclear waste, it's not just, after the reactors. And in the mining process, in the conversion processes, they also generate the nuclear waste. So that's what we will talk a little bit about this as well. Okay, when we talk about the nuclear waste storage. And so that's the other thing I want to mention. The one question I want to ask you is, are all atomic nuclei stable? Definitely, right? And I mean, today when I ask you this question, the response to this, definitely this is a false statement, right? Otherwise, then we don't need to talk about nuclear energy, right? So these are some of these type of reactions, and you will see that it generates different type of particles, right? One is this is a gamma particle. Okay, a gamma particle, there is no particle mass, but in most times it often accompanies the emission of a alpha and beta particle from a radioactive nucleus, right? So this is a beta particle, this is an alpha particle, and then we need to consider, what the problems with this type of particles, right? These are the three main type of small particles, okay, which can be produced by radioactivity. And then the alpha and the beta particles, harmful chemicals in themselves. This is actually a pretty important question for us to understand first. Okay, they are not harmful chemicals in themselves. The answer is they are not. Okay, they are not, but they have an incredible amount of energy of motion. That is a problem. Okay, so if our human body absorbs it, and then it often ionizes atoms and molecules, right? So that's what we don't want to happen. So this is called ionizing radiation. Okay, for example, if we use a human body, the modes of exposure, there are two modes, right? External exposure, right? So this is only on our skin, from our external body, but there's the internal exposure as well. If we inhale these particles, that's what happens, for the internal exposure, right? So inhale, that's definitely right. Ingestion of food, then those type of things. Again, this try to show you different type of ionizing radiation, right? Alpha particle, beta particle, definitely. They are beta particles here, right? Then particle beams, these are different ones, right? The alpha particle, beta particle, neutron beams, proton beams, right? But it also includes the X-rays and the gamma rays, right? So those are all called the ionizing radiation. So of course here, we mostly talk about the alpha and beta and gamma, and then the thing is this type of particles, they are, their effect on our health is different, right? For example, the alpha particle, it has a high ionization density, but then the beta particles have low ionization energy. Gamma is also low, but low, low ionization density, but it has a high penetration power. Okay, so the neutron beams, it has a high ionization density as well. So that's why, for alpha particles, the distance traveling in air is quite short. Okay, so in that way, alpha particle is in certain way is easy as well to protect ourselves from alpha particles. But then beta particles are several meters, and then gamma and X-ray, there are several tens of meters. That's more challenge, right? This schematically showing this, right? Alpha particles, we can just put a piece of paper in front of us, and it should be okay. Beta particles, and it's more difficult, right? Then, for example, the medical X-ray, then it can transmit, more long distance, gamma ray, neutron. You can see the difference here, right? So it's good to know a little bit about this, so it will help us to protect ourselves and others, around of us. And then the main thing, in terms of the health effects, the radiation sickness, right? This is our normal cell division, right? So, most of the time we are healthy, right? But if we get the radiation, and then it will cause the cancer cell division, and then you will see how this is, again, this is uncontrolled, just like what we talked about a little bit earlier, the atomic bombs, right? So we don't want to get into this. That's the key thing, right? Yeah, this is some nuclear reactions. I think it should be easier for us to figure this out if we have the theoretical table around of us. But I will give you the answers here, so you can practice later on by yourself. And so how do we quantify radioactivity, right? So that's one thing we heard about these terms. I think most of us should have heard about these terms before. The first one is called RAD, right, which is a short term of radiation absorbed dose, which is the amount of radiation absorbed by the human body. And 1 rad is the quantity of radiation that deposits 0.01 joule of energy to 1 kilogram of body tissue. Okay. You will see this, right? This is not really, by this definition, this is not a particularly useful quantity because the damage inflicted by 1 rad of alpha particle is actually equivalent to 10 to 20 times that by beta particle, right? By this definition, it's only talk about 0.01 joule of energy, right? But we don't know where the energies come from, right? From which type of particles. So then there's a new term, it's a REM, Roentgen equivalent demand. Okay, this is a scale of absorbed radiation that incorporates the biological effectiveness factor, right? So this is you see the biological effective factor for alpha particle and beta particle is different, right? But this REM is taking that into consideration. And then there is another term as well, another unit, sievert. 1 sievert is actually equal to 100 REM. And then, normally where we get the radiation, right? So here actually schematically showing that, okay? So we get 82% of the natural background radiation, okay? And then 18% is actually from the man-made radiation. And then among that 18%, and then 58 will be from medical X-rays, right? When we, for example, when we go to the dentist, right? Then the nuclear medicine, that's 21%, and then 16 will be from the consumer products, that from the occupational fallout and the nuclear fuel cycles, right? So that's roughly about it, we all got the radiation. For example, the annual radiation is the 0.3 rem, and then 55% from radon in indoor and outdoor air. Okay, 8% from cosmic ray from outer space, 8 from rocks and soil, 11 from natural radioactive isotopes of elements that are present in our own body. We have radioactive isotopes in our body, right? That's one thing as well. So in certain way, we actually, if we follow the safety protocols, we don't need to really worry about this nuclear activity that much, because it's always around of us, right? It's actually within our own body, right? So that's the other thing. But of course, if we don't know this, right, if we don't understand, the scientific knowledge, then of course we're concerned more. So one of the important things is we need to understand, if we think about the nuclear waste, the nuclear hazard, is about the half-life. Okay, so here actually shows that the uranium, for example, it has a pretty long half-life. Okay, it is actually, for uranium-235 is 704 million years. That's pretty long, right? There are a couple of key concepts. Every radioactive element have a half-life. Okay, basically half-life is a time it takes for half of its atom to decay. So that's why you see here, if we consider this is for uranium 235, this is per 100 atoms, that's 100, and then when it gets to 50, that's the half-life. Okay, and then the longer the half-life, the less intense the radiation. Normally after 10 half-lives, an element is usually harmless. So that's a 10 half-life, right? Depends on how long, what is the half-life. So, but half-life, that's it's important. So that's why in this, you talk about the lethal legacy of American nuclear waste. So we're slowly getting back to the nuclear waste. One question about this is, radioactive decay of an atom in an isotope sample occurs all at once, true or false? Right. Of course, this is false, right? That's why we talk about the half-life here. And so this is one thing I showed you earlier, and yeah, so this is related, but then this is a question related to it. Given the half-life of plutonium 239 is 24,000 years, how many years will it take for the level of radioactive from plutonium in a sample to decrease to 1 to 288, okay, which is about 1% of its original value, right? So how do we calculate that? So I want to put this question, exercise question here, is because it's related to half-life. The equation, related to half-life. So basically, right, we know the half-life here actually, right? And then how do we get the K value, right? And that's how we, this is related to half-life, right? Because there's a log here. So from that, and then we can calculate the T, which is, if it decrease to 1/2, and then that is how many years it will take. Okay, but there's an easy way if we are pretty sensitive to numbers. 128, Okay, and also this is related to half-life, right? So 128 is equal to 2 power 7, right? So that, to get to this level, that means it will take 7 half-life period are required. So if we go this way, you will see this value is pretty close to that. Okay, that's a quick process. Anyway, and then the next question is related to recall from introductory chemistry that for half-order processes, the fraction F of reactant left after time t of reaction has a collapse is given by this equation that I already showed you in the previous slide, which K is a rate constant. Calculate the time required for 99% of a sample of uranium-238 to disintegrate. So, so the relationship between K and the half-life is based on this, right? And we also already use this as well. So to get to that, right, so we need to find out the half-life of uranium-238, which is 4.5 times 10 to 9 years. So from this equation, then we can calculate the K, right? Since we know we can find out the half-life of uranium-238, and then we can use this equation to calculate, the T, and which is here. Okay. Of course, for F, how do we get the F, right? This number here, because this is required for 99% of the sample, right, to disintegrate it. That means F, this is whatever left, right? So F here is 1%. That's why this is a 0.01. Okay. So yeah. So this related to this figure again. Okay, which of the elements in this 14 steps? Actually, there are 14 steps here. Sequence of uranium-238 radioactive decay is a gases, right? So far, we probably think about, oh, okay, all these are metals, right? But one of these is not, and that is random, okay? And yeah, random, it has a half-life of 3.8 days. And is in some areas, if we have a lot of rocks and granite there, in those areas, the random level is actually pretty high. At least in US, there's a safety measurement for that. So in some areas, in their houses, they have certain ways, to get this level lower. Basically, we need to keep a good air circulation. So that's one thing, and so it could become an indoor air pollutant. Okay, so that's the other thing. Let me see the time. So we talk about the nuclear radioactive effects. I think we are about, Dr. Ahmad, right? We are about the 1 hour mark.
You want a break?
Yeah, we can do that if that's okay.
So welcome back to all the participants. So after the short break, so now I hand over the session to Professor Mao. Mao, please.
Great. I hope everyone has a good stretch. So yeah, let's go to nuclear waste and really start looking into this. So I think the first part of this lecture really, I think it helps us to understand the nuclear reactions, the nuclear process, nuclear power generation process. And so now I think it's a little bit, it should be easier for us to understand the nuclear waste. So as we talked about, right, the uranium-235, right, then, goes through the nuclearization and fission process, and then it generates this type of elements, right, plutonium, cerium, strontium, and other IUN elements. Basically, these represent the metals, right? So, and then those are the dangerous, they could emit dangerous radiations. That's why we need to consider, taking care of the nuclear waste. So that's why, and then, there are in this field, it is categorized by high-level waste and the low-level, waste, intermediate level waste. So this, of course, because it's a high-level waste, so the most dangerous radioactive waste. So even though earlier we talked about 1 gram of uranium-235 can generate how much power, right? But then spent fuel comes from nuclear reactors now it's 52,000 tons, okay? And so that's the spent fuels. And then they are also liquid and solid waste. For example, from plutonium production, which is 91 million gallons, right? Then you see here that the liquid, and about 70% of the available storage space is now filled with used fuel assemblies. This is at the Tokeer point. This is one of the nuclear power plant in US, which is at the tip of Florida. And so that's why, this gives us really alarming signal that we have to take care of this nuclear waste. And and then, there are transuranic waste, okay? That is, including clothing, tools, and other materials contaminated. Basically, this is from the contamination. And then there are low or mixed low-level waste, which includes the radioactive and the hazardous waste from, for example, hospital research institution and decommissioned power plants. Okay. So, for example, Tokeer Point, okay, that's power plant produced annually on average about 2,500 cubic feet of low-level waste. So that's, again, that's a lot, right? And then during the mining process, there's something, it's called the uranium mill tailing. And basically, those are the residues left from the extraction of uranium ores. Then you see here 265 million tons. That's a lot. This shows actually some of the details, especially in terms of the uranium mill, how it is. It is from a long way, right? The whole crushing, sampling, grinding, and then going through this leaching process, right? Basically, this is more related to chemistry part already, right? But the important thing related to here is I want to show you, I want to remind you is about the tailing, right? Then it goes to the tailing piles, that's how this is. It's a complicated process, but then here I want to show you right now, for example, US, it doesn't generate all the uranium fuels by itself. It's actually a lot of it is actually imported. So here you can see that, right? 21% is from Canada, 18% from Australia, and then only 12% is US, and also 12 other countries combined. Okay, so that's the reality, and also the uranium for US nuclear power plants, you will see this there's a huge change now, right? So in the 1950s, okay, mostly is from the domestic concentrate production or purchase the imports, right? The certain time is actually is only from domestic, but then started in the late 1980s, and then US actually power plants purchase from domestic suppliers. So this is, that's three sources now. And then you will see that the domestic concentrate production is actually pretty low. And so that's a big change. The other countries, maybe, this is a situation different, but that's happening in US. So nuclear waste storage, because of those nuclear waste, and so the overview, and this is what happens, running out of the current methods of storage are running out of space and are not intended for long-term use. So this is related to nuclear waste containment. Actually, we try to solve this problem. So how can we keep it for long-term? Okay, long-term means 100,000 years. Okay, it's not like 10 years or something like that. In US, actually, there is it's called the Nuclear Waste Policy Act, which was established in 1982. So that is an act to provide long-term storage for nuclear waste. So far, the federal government has scrapped Yucca Mountain, and it considered the alternative storage methods. Okay, and then I will talk a little bit more about this. And then in US alone, it has more than 64,000 metric tons of nuclear waste. How much it is enough to cover a football field about 7 yards deep. Okay, then half-life of the fuel is more than, right, we talked about this earlier, 1 million years, right? Then again, the legal requirement is the Nuclear Waste Policy Act. We will get a little bit more details about this. So this is a really one slide. I like this very much. This is really a very concise summary of everything we are going to talk about today. But one thing I want to mention is, in average, right? It's generated nuclear energy. It's about 10% of the total the world electricity, right? Then this part, okay, this part is going to work in more details about this. So this is what happening, in US in terms of the use of nuclear fuel in storage. I mean, if you remember the map I showed you earlier, where the power plants are in US, and this is more or less coordinated with that, right? For those states, have more power plants, it has more nuclear waste, right? For storage. So that's no surprise. The other thing here, I want to point it out here. You will see Nevada, it has zero spent fuels. Okay, even the Yucca Mountain is actually in Nevada, right? We'll get back to that. Why is at zero yet, right? So these are the few places, with those nuclear power plants and the storage sites. Okay, so this is a really, a situation for us to consider, and then because I'm a chemist, so this is a magazine. It's called the Chemical and Engineering News. Is talk about the combating corrosion in the world's aging nuclear reactors. So it's not just about the nuclear waste, okay? There's another issue with nuclear power is related to the nuclear reactors. Many of these nuclear reactors was built, 50 years ago, or more than 50 years ago, right? You can imagine, for these reactors after 50 years, right? It's still working, or how much longer it can keep working, right? So this is really a concern. So that's one thing, we need to look into this. So the storage options, this we'll talk about this a few aspects. Spent fuel pools, right? Then the dry cask storage, and then in terms of long-term storage, Yucca Mountain, we will talk about this, and the reprocessing. We already mentioned that a little bit. We'll get into more details about this. Okay, so the spent fuel pool, a pool, right? So that's in that way the easiest to understand, and also because this is it will be stored in cooling ponds, right? So because it's also close by to the nuclear power plants, so we call this on-site as the reactors. Okay, so the good thing about this is protect the surroundings from radiation. So then you will see that this is the number of field poles among the years, and they keep increasing. The problem with this, right? We're running out of space, right? So that's why, and also this is only intended as a temporary solution, right? So that's one thing we need to realize. So that's why the second one is called the dry cask storage. So we basically, we surround the nuclear waste by inert gas, steel, and concrete, right? So they don't leach out, they don't move to other places, they don't get into air, right? But it's not like anybody can do this. It must be licensed by NRC, Nuclear Research Council, right? So far in US, there are 22 different licensed designs, and 9,000 metric tons are stored this way. The problem is, this is only variable for a certain number of years. Right now, they are licensed for 50 years. Okay, so every 50 years, it could need to be licensed by the NRC, right? And then because this is offsite, this is not on-site solution. So then, the transportation to offsite is difficult, right? And the other problem is a potential terrorist target, right? So that is actually, if we look into these casks, this is a design, how complicated this is, because this is supposedly for 1,000 years, right? So, and then, there are many of these just layout side, you can imagine, right? The effect, by the weather, so of course, some of these are not exposed like this, okay? But this does exist, okay? Surprisingly, and supposedly, right? By this method, it should go through, either at or near surface, and then, but most importantly, it should be stored in geological repositories. And so sealed, and then it is on the ground, and so safe. So in this way, it's safe with reduced active matters. So that's the long-term goal. So this is, if we have a little bit more time, we may not go through everything. This is a timeline for nuclear waste storage in the United States, right? The nuclear power plants started to be built, in the 1950s, right? And then we talked about this in 1982. There's the Nuclear Waste Policy Act, and then this Department of Energy started working on this, and then started this Yucca Mountain for a national repository. But then, of course, this didn't go well, and so you see all these are related to this Yucca Mountain. And then, yeah, even today, there's still a lot of discussion, and even, in the a few years ago, then the government started to resume consideration of Yucca Mountain. Okay, so far it haven't been used. That's in short term, that's what it is. And yeah, so let's talk a little bit about that, right? The government, they spent a lot of money to build this, okay? But because, and then approved, by Congress, by U.S. Congress in 2002, but then canceled by President Obama in 2009, and then potential alternative sites are being considered. Then there were even a Blue Ribbon Commission on the American nuclear future. But then the problem, so these are the two sides of this, okay? So a lot of people worried about this. Okay, right? If we put this in the Yukon Mountain, it was still leaching out. But there's a supportive studies, in the history. For example, here about 2 million years ago, this uranium in carbon was caught in a chain reaction. Plutonium was produced and trapped in the rocks, right? Here shows that what happened. Since then, the radioactivity has moved only slightly, and the plutonium was devolved into non-reactive substances. Okay, so in this support the idea that this dry cask storage is a good way to do that. But then, of course, Nevada residents don't like this idea. So that's what is this Olympic step in. It's called not in my backyard. So that's why there's a lot of protest, and that the government couldn't make this happen, and even spent a lot of money there. Okay, and so that's the status related to this. And then there's a reprocessing. I mentioned a little bit earlier. Only after the processing, only 3% helical waste remains, and the results are mostly plutonium and some uranium-235. The current capability is only about 1/3 of the world's fuel, right? So basically, after reprocessing, this fuel can be reused. So that's the process. And here actually shows the whole process, right? From mining and go through this, and then spend the fuel reprocessing, and then it can go back. Then we can reuse it. So that's the process. How this is done is mostly through this long-term process, right? So the spent fuel starts from here. So it basically, similar to the mining process, right? The sharing, dissolving, and then separation and purification, go through the whole process. And of course, this part related to the chemistry side, right? So what is the chemistry in this reprocessing process? Basically, we dissolve the these metals, and then use this molecule to combine with the uranium plutonium ions, and then we will be able to enrich them, and then for enrichment, and then we can reuse it. So that's the basic process. This is called the Purex principle, right? So TPP, this is molecule is called the TPP, and so that's the process. Okay. The problems with this reprocessing, so you spend the fuel, but after processing, it's stored in powdered form. In powdered form, which is not ideal. That's the problem. And then after processing, is significantly less radioactive, but it's hard to keep track all of the materials at the reprocessing facility. So that's also there's an incredibly high price tag. So perhaps about like $100 billion to reprocessing the existing spent fuels. So there are some studies actually mentioned about the reprocessing is more expensive than mining. So that's also what I'm trying to show you here. That's why there's a resistance to do the reprocessing. That's the other problem. So so that's one thing I want to mention about. I want to mention, just show a couple of lines related to the nuclear waste, this act. So you can see that this need to go through a lot of regulations. So that's the details. I will skip this part for now. But the important message is that is likely this is a long way off, because no one wants it in their state, right? Even though there's a federal repository, planned, but it's very difficult, at least for now. I don't know how, this issue will be solved in the US. In some other countries, maybe it's easier, but in US, this looks like it's pretty challenging. And then one important thing is reprocessing provide an interim solution. But then, even the U commander is finished, it will only hold 70,000 metric tons. So this is what currently exists. They would fill it up, right? And then what's next? So I need more sites. To summarize, to get everyone a little bit idea, the spent nuclear fuel composition, 95 is actually uranium, 3% is fission products, and 1 to 2% is other actinide elements. And then we talk about this Purex process, right? This is another way to look into this. Now, so that's nuclear waste storage briefly. I want to get back to this. Some of you already asked about the nanocrystals, what nanoparticles, how this related to nuclear waste containment. So now we are getting to that. Okay. I think that was 2 or 3 days ago, we talked about this type of compounds, A2M2O7, right? There are several important properties of this type of materials. There's thermal stability, viable host, radiation tolerance. That's very important, right, for nuclear waste containment. And also because the compositional flexibility, the functional versatility. So that's what we are getting back to. We consider this is a very important, useful material for nuclear waste containment. So let's try to finish this part related to the synthesis of this type of materials. I was trying to talk about, using modern salt synthesis, right? So it's quite a simple process. The reaction temperature is low. So this is the process we did, right? Basically 2-step process. I talked, the other day. So let's go through the co-precipitation process, and then go through this modern salt synthesis process. If we have nuclear waste, we can also add it in this step, right? We can do the co-precipitation and then, do the modern salt synthesis, and this temperature is relatively low, right? That's also important, for nuclear waste. We don't want to heat it up to too high temperature. So that's an advantage. So basically, with our nanocrystals, and then, the whole process lowers than the temperature. And also I want to demonstrate that, we can actually add a lot of nuclear waste into this type of material, into this A2M2O7 nanoparticles. That's the other advantage of this. Here I want to, basically I want to, finish up the synthesis process, right? I mentioned earlier, for this type of materials, depends on the ionic ratios of these two, and it could be a fluoride structure or pyrochloride structure. So here we look at this 6 compositions, and basically with different A-site elements, right? And so we look at it into the synthesis, and the synthesis is actually more complicated than initially what we thought, because for example, here we use a hafnium, right? Hafnium oxyhydroxide is precipitated at pH 5, but then for yttrium, gadolinium, erbium, and ruthenium is precipitated also around 5 or below 5. But these elements, they don't precipitate as just hydroxide. It actually has this composition. But for these two, they precipitate at hydroxide, but then the precipitation pH is much higher. So that's why for the precipitant here, with this general formula, for these 4 elements, we see from the TGA, we see a very smooth, decrease of the weight. But then for these 2 elements, A-site elements, and they are 2 regions for the weight loss. So that's consistent with, with these two elements. Actually, the precipitate is not a uniform process. So that's one thing I want to mention. And also we did the other thing is how do we compare, right? Because so far I was trying to talk about the modern salt synthesis is a wonderful process, right? We got this precipitate, right? Can we do the direct calcination and what the difference that will cause? So we wanted to understand this process, So we did have quite a lot of study. Okay, this is a busy slide, but don't worry about it. Don't worry about a lot of details. I'll walk you through this. So DC, we use the direct DC to represent the direct calcination. So you will see, for example, I'll pick this one, and so for this one, you will see for the non-certain half-life, right? By this direct calcination of the precipitate at 650 is amorphous only when the temperature reaches to 1,000 or 1,500 degrees Celsius, and then we will get crystalline samples, right? The other ones, more or less have this similar trend. And then we also did the Raman spectrum, and you will see that, if we look at the non-certain half-life again, at 650, this is more or less amorphous, and then after that, we'll get this, this is a pyroclore structure, right? Only at a high temperature, we can get to that, right? So this is what we try to summarize. Expected is based on that, that formula, right? If the ionic radius is around, below 1.46, right? It will be the disordered fluoride structure, right? For this one that's here. And then, from the direct calcination, we can see that, this one's, we actually don't know what crystal structure is. But then after 1,000 degree calcination, and then we got the order of the pyroclore structure instead of the borderline, and this also pyroclore structure instead of the fluoride, expected fluoride structure, right? So this is the synthesis, through our, through the direct calcination of the precipitate. And here actually shows, with a different temperature, these particles, how their size change, the morphology change. Definitely, especially from here, you can see clearly the particles size increase, with higher temperature. Then how about the modern salt synthesis, right? And we can see that, even though this nanoparticles were synthesized at 650 only, right? All of them actually show the crystal structure, okay? So that definitely shows that the modern salt synthesis can lower the synthesis temperature quite a lot. And also, for the particles synthesized at 650, we can take the Raman spectrum, and we can see for these two, we already got this pyroclore structure, crystal structure. And then from the SEM images, we can see actually the nanoparticles. So if we combine the results from these two synthesis processes, and you will see that by the modern salt synthesis, for these two, the praseodymium, lanthanum, carbonate, and we already got the pyroclore structure. Even the synthesis temperature is only 650, right? But then for this one, for the other four, they are fluoride structure. And then for the direct calcination, for these two, only, after like a temperature at 1,000 degrees by direct calcination, and then we get the pyroclore. But then for this one, we can convert this at high temperature into the pyroclore structure. So that's basically, tells us, how these two combined together, right? So that's related to the synthesis. I just want to finish up, because the other day we couldn't finish it. And get back to uranium. Uranium, is actually quite a complicated, element. So here shows that in terms of the oxidation state, it has a +3, +4, +5, +6. Okay, +4 and +6 are the most common ones. So it can exist, in oxides, in this in different hydroxide, with for +4 and +6 oxidation state. And for example, if this is actually +6 as well, depends on how it combines with other elements. It has this type of polyhedrons. So again, if we want to use it for nuclear waste immobilization, so then we have to have a suitable nuclear waste host, right? So there are a couple of criteria to choose for that, right? So the first thing we consider is a large containing capacity. That means, for uranium, we want to be able to add as high as possible uranium content into the nuclear waste host, and the high thermal stability and the good radiation stability and the high chemical stability and resistance to radiation-induced thermophilization, negligible leaching, right? So here I want to show you some studies we did, to prove these 3 criteria. That's what we're going to do. And here, this is from our study showing that we can dope different amount of uranium into this type of non-standard half-net nanoparticles. Right. For example, here we showed from low to high, up to 30%. So, and the materials, they are pretty good. So then here I'm trying to show you actually, in terms of this, the Raman spectrum, and you can see that, the uranium, different ions actually preferred, okay, at the different doping levels. And when the doping levels was getting higher, and then, uranium ions actually have different forms. And this is related to what is called the speciation. And Raman spectrum is actually a very unique technique. And also I will show you the photoluminescence spectrum also can be used for that purpose. And if we consider the intensity of this peak as I1 and this is I2, and then we can plot something like this. And then you will see that with the increasing concentration of uranium, and this ratio actually, increasing. And then we also did the XPS, and we can see that, there are uranium 4+ and uranium 6+ in this nanoparticles, right? Depends on the doping levels of uranium, and then we will see the ratio of uranium 4+ and the uranium 6+. It varies, and here actually we plot this, in terms of the ratio of uranium 4+ and uranium 6+ with the concentration of uranium. You will see that, right? With the increasing the amount of uranium, and then uranium 6+ becomes more dominant. And and then as I mentioned to you earlier, the photoluminescence spectrum is actually can also be useful for speciation of uranium as well. And so yeah, these are the original photoluminescence spectrum. And here I'm trying to show you the ratio of this uranium 4+ and the uranium 6+, right? With concentration of uranium as well. And so you see this is also decreasing based on the photoluminescence spectrum. Remember, this is quite similar to this plot as well, right? Based on the XPS studies. So this type of results, they support each other about, the non-standard half-net is very good uranium host. And the other important thing is in terms of the thermal stability, right? So here, so far, I showed you, we really can dope uranium to high concentration in non-standard half-net, right? The next thing is about, the thermal stability, right? Here shows that, so here again, okay, we picked the 10% uranium doped national half-net as the example. So at the room temperature, so we have this structure here, right? And then heating up to 950, okay? So it changed, right? From this Raman spectrum, we can see that, right? That's increasing. This is the heating up process. And then, we cool it down. And then, at a certain temperature, we take the Raman spectrum again, right? So the interesting thing is once it reaches the room temperature and we compare this spectrum here, it's the same as this one, okay? So if I show you schematically, the room temperature, it has a coconut structure, and when it reaches the 950, it has a pyroglow structure. The important thing, this shows this heating up, this showing the cooling down. So this can be recycled. That means, this national half-net has very good thermal stability and is also recycled, right? And so that's related to the thermal stability. And then the other thing is in terms of the radiation stability, right? So we use the gamma ray to irradiate our nanoparticles and to see how stable the nanoparticles are. Yeah, again, this is a busy slide, but that's fine. We can look into this. So we look at the six A-site elements. So yttrium, lanthanum, praseodymium, gadolinium, erbium, and ruthenium, right? These four, figures actually correspond to that. But the most important thing is you see there are four patterns here, right? So that's related to different doses of the gamma ray source. Okay, let's look at this number, and then based on the XRD patterns, we can calculate the particle size. And here we can show that the particles actually are relatively stable. There are some outliers, but in general, the particles didn't change that much. The patterns, we didn't see obvious changes, right? You can see here. And then we also use the Raman spectrum to look into this, whether there are any changes. Right? More or less, we didn't see much change, but there are a couple of samples, for example, this lanthanum half-net, and actually initially is a pyroglow structure, right? And this dose, and then it looks like it becomes the fluoride structure. And then with a higher dose, and then it becomes the pyroglow again, right? And then for this one, this is the lieutenant half-net. Okay, lieutenant half-net then is the opposite, right? So it's a fluoride structure, at this doses, and then it becomes a pyroglow structure, and then higher doping level at doses, and then it becomes the fluoride structure again. But then for the other ones, it doesn't change that much, right? So based on the results we had, for lanthanum half-net, so it has this circle, right? It starts with ordered pyroglow structure. After certain doses, it becomes a disordered fluoride, and then at the higher dose, it gets back to the original ordered pyroglow structure. For the ruthenium, it has the opposite trend. So we've been wondering, right? Why there's this huge difference. So we believe if we look at the atomic structure, right? The lanthanum 3+ it actually has F0, right? For the ruthenium 3+ is F14, and while for the other four, they are in the middle, in between of these two cases, right? So we believe that makes a difference. And even though the most studies less way, right? So and also we look at this, in terms of the photoluminescence of these samples, and so you can see that for some of these samples, mostly we look at the intensity of this transition, right? So you can see with the different doses, for some samples, especially like for this one. So there is a decrease of that the emission intensity, and then at the end, there is a slightly increase, but there is no very smooth trend. That also makes this for this type of materials need further studies. But in general, the three key points I want to show you here is, we can dope high levels of uranium into these type of nanoparticles, and also they are quite thermostable and also gamma ray stable. So that's the key point I want to show you. This could be a very promising nuclear waste containment material. So with that, and then I want to acknowledge my research group, my former group members, and also my collaborators and the funding. And if there are any comments, any questions, for now, I think we can close. I would appreciate that.
Thank you, Professor Mao, for the very interesting lecture on the nuclear waste. So I request Dr. Ufana Riaz to please come up, and if there are queries from the participants, so please ask Professor Mao on behalf of our esteemed delegates. Dr. Ufana.
Hello, Professor Mao. Hope you're doing great. So there are many
Thanks.
questions. I'll take up one by one. What are the nanocrystals used to contain nuclear waste? And what are the necessary conditions that can be adopted to minimize the nuclear waste when we synthesize nanoparticles?
So yeah, so let's get back to this this slide. And those are the criteria, for a good nuclear waste containment materials, right? So the result I was trying to show is that these materials, these nanoparticles are potential, for that purpose. Yeah, but of course there are much more study need to be done, right? For example, the long-term stability, right? The chemical stability, whether there is any leaching as well. So those type of studies we haven't done yet. So yeah.
So what are the chemical treatment methods that we can use to minimize the nuclear waste management and to avoid the harmful effects?
Yeah, the main thing is we should try to keep them as in the solid state, so they won't leach into water. That will become even a more serious problem, because once they are getting in water, right, they will get into underwater, and they can go anywhere, right? That's really a concern. So that's why this nuclear waste storage sites, they mostly are, are designed at those dry areas, and and also they should have less people live in those regions, and so they won't get into our water system. That's the main thing. And even in US, there are some accidents that happen like that.
So is it possible to introduce non-metal based components in nuclear waste management to avoid exploitation of metals in waste management?
Yes, definitely. So again, we will get back to that. I know some of the participants ask about this, right? So for example, right now people are trying to explore, morphs, for example, for this purpose. Yeah, even though the long stability, that's a concern. Because morphs, is not as stable as the metal oxide nanocrystals as I'm showing here. But the morph shows very high absorption capabilities. So that's the other, that's the advantage of that. But the long-term stability, there's a lot of concerns. Yeah, I mean, again, overall, in terms of the nuclear waste immobilization, containment, scientists just explore different ways, and try to find the different materials, hopefully we will be able to solve this problem, in short term, and that will really help a lot.
Okay, so please enlighten about the idea of information communication technology applied to radioactive waste management.
Mm-hmm. Yeah, I mean, again, this is one is, I think the other thing is, because I spend a lot of time to talk about the background of nuclear chemistry, nuclear energy. So this type of information will be very, very useful to the public. So each of us can, try to talk with the general public, and that will help. Then the other thing is, I think we should try to avoid those huge accidents. Each time when that type of thing happens, we all worry about it, right? For example, Fukushima, right, that accident right now, there's a lot of report, right? The nuclear waste actually dumped into seawater, right? That's really a concern, not just for people live close by, right? Then it will affect the fishes, and then it can go to other countries, right? Because it's water, right? So that really causes those type of, we should try to avoid that. And then in terms of the science, I think we should, spend more time to find the solutions, not just for solid nuclear waste, but also for water as well. I think there's a lot of things we can do, and of course, this also depends on the funding provided by the government. So all these are connected. Then, funding not just to do the scientific research, right, is also to raise the public awareness about the nuclear energy. So all these are important. While it will take time, it will take a lot of effort, but I think that will be worthwhile, something worthwhile to do.
The next question that I'm taking up is somewhat related, that somehow we are exaggerating things vis-a-vis the nuclear fuels. So should we not work to sort out things rather than worry about it?
I think we should, really look into it and try to understand it. Then, it's just like things, happening in our daily life, right? If we don't know the reason for certain things, we will worry about it more, right? If we understand it, either it's scientifically or not scientifically, and then, we will worry about something less, right? So I think that's why, I appreciate this forum. So for me, gave me this opportunity to speak with you. I hope, it helped in a certain way. If each of us can do a little bit of something like this, it will be very helpful.
What amount of the nuclear waste is holded by the Yucca Mountain?
Oh, the Yucca Mountain is actually, it's not being used yet. That's a key point, because the local residents protest to to transport the nuclear waste from other places to Yucca Mountain. Okay.
Oh, okay. And how harmful is it to decompose nuclear waste in oceans for aquatic species and environment?
Yeah, that's why I was trying to say. Let's try not to get the nuclear waste in the water. That's really, I think that's really a difficult issue, because water is so difficult to contain and so large amount. Seriously, I don't think there's anybody have really a solid answer or solid solution for that. I think the best strategy is to control the source. So let's do not get waste, nuclear waste into our water system. Not just ocean, even into our, rivers. Don't dump nuclear waste into water anywhere. I think that's something I could say now. Yeah.
So how much amount of investment is being done worldwide to combat this nuclear waste management?
How much? Actually, I don't have the exact numbers. Yeah.
I mean, are there any projects that are going on? I mean, is it a serious concern? Is it gain popularity? I mean, are people aware of it?
Yeah, I think definitely. But at least I heard some news reporting about the Fukushima the nuclear power plant. Even recently there was some news on there are something on the news.
Okay, I think we are done with all the questions. And we are very delighted to have this lecture because it was really unique in terms of information, in terms of awareness. I mean, it was in tandem with the storage and energy generation. So at one point we are thinking about generating and restoring energy, looking for sustainable resources, and the other part is the in tandem with it is the nuclear waste management. So it has been really informative for all of us, and especially for the participants. And it's a very, intriguing field. I mean, it has actually waken up most of us, to think about the methodologies that we could adopt to, control this nuclear waste that is being generated, and find remedies to manage it. And we are really grateful to you, Professor Mao, for providing us with a variety of topics, and providing us with some information that will motivate us to go into deeper research into these fields, and to find out ways to generate mechanisms to combat nuclear waste management, to combat environmental degradation. We hope to, we hope to listen more of such lectures from you in future, so that you can keep our motivation on, you can keep our spirits high. And we've been really, enlightened by your lectures, your discussions in particular, the way you have put all the topics together, and the way you have compiled your presentations. It is very informative, and there's a huge demand for your presentations right now. Most of the participants, they want your presentations, they want to go through it again and again and have a thorough study about it. So we are really grateful to you, for accepting our invitation to come to this webinar and lecture series. And we hope to hear more from you in future as well. Thank you, Professor Mao, for being with us. Thank you so much. We are really grateful.
Thank you for your kind words.
Yeah. You rightly said, Dr. Ufana, each and every word about Professor Mao and his presentation. Thank you so much, Professor Mao, for not only delivering your lecture on the very hot topic, but also it is very challenging topic nowadays. And I hope that the delegates who are belongs to the UG and postgraduate backgrounds, they will definitely take this topic as their future course of research. So thank you so much, Professor Mao, being with us. Thank you so much. Have a nice day.
Yeah, thank you all. Thank you all. Yeah. Enjoy the rest of your day, and yeah, I'll yeah, look forward to discuss with you in a couple of days, right? In 2 days.